Hello, everyone, and welcome to today's webinar, Multimodal Characterization of Wide Bandgap Semiconductor Wafers. I'm Christina Jewell of LabRoots, and I'll be your moderator for today's event. Now, today's educational webinar is presented by LabRoots and brought to you by HORIBA. For more information about our sponsor, just click on the HORIBA logo in your abstract. Now, we encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Submit. We will answer as many of your questions as we have time for at the end of the presentation. Also, if you experience any technical difficulties, you can utilize this Q&A box and we will answer your questions directly. Now, I would like to welcome our speaker, Dr. Francis D., Product Line Manager, Optical Spectroscopy Division, HORIBA Instruments Incorporated. For a complete biography on Dr. D, please visit the Biography tab at the left of your screen. Dr. D, welcome. You may now begin your presentation.
Okay, many thanks, Christina. And firstly, let me apologize to our audience for the late start. All kicked in here, and all things my laptop had to do an update at 2 p.m. on November 14th. So apologies for that. As Christina said, my name is Francis D. And I'd like to join my voice in welcoming you to take the time to listen to us in this webinar on wide bandgap semiconductor materials. The characterization of that is. My name again is Francis D., Product Line Manager for our Modular Solutions here at HORIBA. So for the sake of giving us a chance to focus on the presentation, I'll go off camera during the presentation, and then I will come back on camera for the question session at the end. So I'll turn my camera off for the moment, and we will go right into the presentation. Okay. So by way of introduction, let me start with a summary on the talking points here for this webinar. So we'll start by looking at a very brief introduction of wide bandgap semiconductors with a focus on the properties that make them interesting and relevant for many applications, and the markets that are driving these types of materials. Next, we will consider silicon carbide as an example to illustrate the typical fabrication process of these types of wafers. And then we will move on to focus on the yield challenges that are common in the fabrication process. And for each of these challenges, we will consider example cases of the optical spectroscopies and other modalities that are common, are used to both characterize the materials as well as help address fabrication deficiencies. The techniques that we'll consider today include Raman spectroscopy, photoluminescence, time-resolved photoluminescence, cathodoluminescence, and laser scattering, among others. Now, we'll talk about these techniques in the context of addressing or characterizing the major yield challenges of residual stress, defects and contamination, as well as uniformity of the wafers. But it's important to point out that there are other uses of these spectroscopies and others in the fabrication cycle of wide bandgap semiconductor materials, and we will consider that next. Now, finally, we will discuss some of the practical instrumentation considerations that are relevant to performing these types of measurements quickly, correctly, and with ease for wide bandgap semiconductor materials. Now, I suspect that this audience will not really need a detailed introduction as to what are semiconductors, but by way of introduction, we understand that most of the solid matter that can be classified into one of three categories. Now, on the left-hand side of the slide, we've got the metals, which are characterized by the presence of delocalized charge carriers so that they are conducting. Okay, sorry about that. My slides are moving. Okay, now on the other extreme, we've got extreme right, that is, we've got the insulators, which do not have these unbound charge carriers. And in the middle, we've got the semiconductors, which are normally insulating, but can become conductive under special circumstances. The distinctive property of semiconductors being that they have this energy gap that separates the bound versus the unbound states of the charge carriers in the material, and that under special circumstances, these charges can transition from the bound states, that is insulating, to the unbound states and make them the material conductive. Now, silicon, which is perhaps the most popular semiconductor material, has a band gap of 1.1 electron volts. Meanwhile, the materials of interest to us today have much higher band gaps, typically above 3 eV. Along with other material properties, these high band gap endow the materials with special properties that make them attractive for key applications. Now, on this table, to the left of the slide, we show a comparison between two of the standard bearers for wide bandgap semiconductor materials. This will be silicon carbide and gallium nitride. And that's relative to silicon for some of the key material properties that are enablers for different types of applications. This information is readily summarized on the spider chart to the right side. And for the material properties of interest in this case, the higher the number on the spider chart, the better the material for a given application. And a quick look at it makes it very obvious why these wide bandgap materials have a special interest, as they are 2 to 5 times better than their silicon counterpart in most cases. Okay, we have a little bit sensitive slide here. Okay, we are back. All right, and a combination of these materials, material properties explains their strong recommendation for certain applications. For example, the high band gap and high breakdown electric fields would recommend these wide bandgap materials for high voltage applications. And similarly, the high melting point and thermal conductivity makes them quite appropriate for high temperature applications. And finally, the almost double, the saturation velocity, which is almost double that of silicon, makes them suitable for high speed applications. So this application information is summarized here in this picture, where you can see that thanks primarily to its high thermal conductivity, amongst other things, silicon carbide makes the best recommendation for high power applications. And you would find them in things like power inverters for electric grids and electric vehicles. Meanwhile, gallium nitride has a marginal superiority in terms of the saturation velocity, which makes them suitable for high-speed applications such as data communications as well as consumer electronics. Now, today, the technology landscape is changing very rapidly, whether it be alternative energy, vehicle electrification, or data communication needs. And in anticipating things like AI, all these applications have a strong demand for chips that start out as wide bandgap semiconductor wafers. Now, this explains why there is a projection of such explosive growth in the industry that manufactures these types of wafers. Now, albeit, in recent times, there's been, some deceleration in terms of the investments that companies are making, but nevertheless, the trend remains the same. That is an upward slope for many of these materials. Okay, so now let's talk about the fabrication process and the issues therein. And of course, for the sake of an example, we'll focus ourselves here on something like silicon carbide. Now, a good portion of the silicon carbide wafers commercially available today are made from the PVT process, or physical vapor transport, which is a high temperature sublimation process illustrated on this chart here. The result of this process is that silicon carbide boules, which gets chopped off into a nice cylindrical puck, and then the wafers are sliced off from this puck. Now, the wafers get polished into substrates and then begins the process of epitaxy, where the base layer silicon carbide is formed and then subsequent device layers are added depending on the different applications of interest. I should emphasize here that for most of these presentation, focus is going to be on the wafer stage, starting with the substrate, the epi wafer, and potentially the device wafer. Now, the semiconductor business in general has a curious business model in that it insists on high performance at a low cost. Now, high performance typically comes from miniaturization, while lowering the cost comes from working with increasingly larger substrates and improving the yield at each step for these ever larger substrates. Now, for a key material like silicon carbide, we see here that better than 60% of the die cost is related to the substrate and the epi wafer yield. So improving the yield between the substrate and the epi wafer stages is very important to lowering the die and device costs. And the route to yield improvement is better characterization of the fabrication process and the resulting material of the fabrication process. So what are the key challenges that we want to focus on today? Now let's start with residual stress, which are built-in local tensile or compressive forces in the material following substrate or epi wafer fabrication. These stresses can result from many sources. Now you will recall that fabrication of a silicon carbide wafers is a high temperature sublimation process over 2000 degrees. And sometimes there can be gradients in both the growth or the cooling phases that can result in these residual stresses to build up in the material. Other sources of stress could come from the mechanical slicing and polishing processes, or even ion implantation during doping. Now, the presence of stress in a material system is a sign of an excess of energy, and nature's reaction in the presence of too much energy is to act in such a way as to minimize that energy. In this case, it does so by deforming the material to relieve the excess stress. So, you can see why residual stress in the substrate or epi wafer can be a leading indicator of defects and general adverse performance of the device. Now, these defects and deformations can be at best benign, or worse, they can result in distortions in charge movement that adversely affect the device performance. So the goal is to start device fabrication on stress-free epi wafers. And evaluating the quality of silicon carbide substrates and epi wafers for the presence of residual stress is a crucial yield improvement before device fabrication. Now, one of the ways to characterize the residual stress in substrates and epi wafers is through Raman spectroscopy, a technique that relies on the inelastic scattering of light by the silicon carbide crystal lattice. Inelastic because unlike the normal scattering of light that has the same wavelength as the incident light striking the material, the Raman scattered light has a characteristic shift in the wavelength that corresponds to certain unique and well-defined phonons of the material. These phonons are specific vibration modes of the silicon carbide crystal lattice, and therefore the Raman scattered light is a probe of the state of the silicon carbide crystal lattice. In practice, this measurement is done with a laser with a very well-defined wavelength that is incident on your wafer through a microscope objective typically, and the backscattered Raman light is collected into a spectrometer. And that characteristic Raman shift is measured by the spectrometer. Now, in the absence of any stress on the crystal, the nominal position of this characteristic Raman shift is well known, and the reason we are using this technique as a probe for residual stress is that in the presence of stress, this characteristic Raman shift, or Raman peak rather, will shift either to the blue or to the red, depending on whether the stress is tensile or compressive, respectively. And equations such as you see in the lower left of the screen here have been developed, for example, by this case, Tian and colleagues, to demonstrate how we can measure the residual stress, sigma over here, as a function of the shift between this, sorry, as a function of the shift between the stress and the stress-free silicon carbide peaks. And of course, that measurement is usually done across the whole wafer, such as the one that you see here on the lower right, done on our HORIBA LabRAM Odyssey platform. Next, let's move to defects and contamination. Now, the ideal is to make epi wafers that are defect and contaminant free. But of course, we know that the reality is different because processes and materials are imperfect. The task then is to design and for design and process engineers rather, the job will be threefold. The first two is to understand the types and potential impact of defects that can occur for a given process. And thirdly is to map or understand the location of any sort of defects on a given wafer. Now with this information and for a given application, they can then proceed to calculate the die yield for that application. For example, in this illustration, we show the defect map for a given epi wafer. It is color coded. The black could mean benign defects and the red could mean killer defects. And when we overlay the defect map of the die, or of the die map on the die map, we can see, for example, that the yield, what the yield could be. In this instance, it was determined that no device or die can have more than 2 defects. And so we can see how we produce a 94% yield. That is 62 out of the 66 dies in this case are good. The goal is, of course, is to use that, use what, sorry, I just had got a blank screen here. I'll take that again. So the goal, of course, is to use whatever was learned during each of these steps to improve the process the next time around in the ever-present drive for yield optimization. Now, in the specific case of silicon carbide, as shown by this data here, Chen and colleagues have done a very good job of characterizing here the typical types of defects that can occur in this material system. Now, starting from substrate BPDs or basal plane dislocations that propagate into the epi layers or transform into threading edge dislocations or stacking faults. We also have things like threading screw dislocation shown in this picture here. Now, whatever the defects, the job is to characterize each of these types of defects, understand their impact on device performance, and proceed from there. And these guys have done a very good job in documenting what these defects would look like under different measurement modalities. But more importantly, they have summarized the effects of each of these types of defects for different device architectures, as well as the severity of each one of them. For example, and regardless of the particular device architecture, you can see on this graph from this table on the right that the thing you don't want to have are things like micropipes or card defects. These are always bad news. And going back 15 or so years, one of the great pioneering successes of the company Cree, which is now Wolfspeed, was really the ability to make large wafers, it's like 200 millimeter wafers without these the famous micropipe killer defects. Now, regardless of the defect type in question, we show in this table that there is a great suite of complementary techniques for their characterization. And the choice of which one to use in any instance is determined by considerations such as the speed of the measurement, the sophistication of the measurement or ease of use for that technique, the spatial resolution that can be derived, and whether it is a surface or depth profiling technique. Of course, cost and occasionally whether one is interested in static or dynamic phenomena are considerations for the choice of a technique. Now, first thing when it comes down to making a choice is a recognition that semiconductor fab time is expensive. Therefore, speed is always of the essence. So it is common to always start with the fastest technique possible And in this instance, one of the winners is photoluminescence. It is fast and relatively easy to use. It can offer a micron level resolution and can do both surface as well as occasionally depth profiling. And it is great for characterizing all the the various defects that we showed in the previous list. For example, in this image here to the left, we show a high resolution PL map of what looks like a carrot screw. So that's the coarse map on the top left and bottom left, and somewhere in the middle there, you can see the high resolution map of a small defect, which looks quite similar to what would be considered a carrot screw defect. Oh, sorry, a carrot defect. Of course, due to the shape of that defect. Now, another technique that has speed in its favor is the laser scattering technique. Now, I should say that this is not quite common, except you'd find them in optical inspection tools, so laser scattering techniques, and this is what we use here. And this data was collected on the HORIBA PDX Padian. And just to be clear, this is an inspection technique where a laser is rapidly rastered across the wafer, and a detector picks up the microscopic scattering of surface defects, keyword being surface, at a very reasonable resolution. It generates a defect map, and the visual image of the defect at each point can be cataloged. Right? In this instance, we can see that it was able to pick up things like micropipes, particle, and scratch defects. Now, the great benefit of this modality is speed, but often one may not be able to fully characterize the specifics of any given defect. So you can start as a kind of a first line measurement to pick up whatever is obvious, and then use another modality to further characterize it. And talking about using another modality, for example, we can leverage the defect map generated by the laser scattering technique shown on the previous slide, and one could dig deeper into any one of the particular defects that we saw there using a high spatial resolution tool, such as cathodoluminescence, shown here, or CL. And CL is a modality that is often on an electron microscope, because it leverages the electronic excitation of the electrons from the electron microscope. And of course, it's quite relevant here because we are talking about wide bandgap materials. And so the high energy electron excitation often provides enough energy to straddle that wide bandgap for wide bandgap semiconductors. And also this technique can also be, because electrons penetrate deeper into the sample, can also be used as a quasi-depth profiling technique. So its drawback is that CL is often, it's not a starter technique. It's being on an SEM, it's a fairly sophisticated piece of instrumentation. And also you would need some very custom stage modifications to handle large wafers. So that you tend to use coupons. And in that sense, it can be slow. So we'll come back to Raman spectroscopy as another technique for looking at defects. In this instance, we are showing a correlation between the high resolution defect map of what looks like a micropipe defect, which is what you see on this CL image in the middle of the page, the grayscale image here. You can see what looks like a micropipe. And we can correlate that measurement with Raman spectroscopy, which is the color coded image that you see to the right of that grayscale image. And what we are seeing here is that the micropipe defect is very, the high resolution of the SEM, it clearly shows what the micropipe is, but it doesn't give you any sort of environmental information around that. But Raman would very clearly show that by displaying the stress map around that defect. And one can have a much richer set of data that characterizes the surrounding of the defect. In this case, you see the stress map, and you can see where is tensile, where is compressive, and you get a sense of what's really going on around that defect location that can be addressed by material or process. So here's another illustration of the use of Raman spectroscopy for effect characterization, and I'll use the opportunity to provide a shout out to my colleague, Dr. Fran Nadar, who just shared this data with me. It's very hot off the presses. And this is a silicon carbide wafer, and it's just looking at various defects. And I show this data here because it adds one more dimension that the previous one did not capture, which is the confocal, using the confocality of the Raman microscope to probe the depth. So you can actually figure out the geometry of various defects. So if you look at this data here in the middle of middle of the screen, Fran is probing here from the surface of the material and going in about 1.5 microns below the surface. And first we can see the geometry around the defect. It's basically bulk material. She has a Raman signature from that. And then, probing at the defect, she has both the signature from the bulk surrounding bulk material as well as the peculiar signatures of the Raman of the defect itself. And with our software, you can take the separate sort of the difference of the two, which is the blue curve that you see at the top, the blue spectrum that you see at the top there, and that's really, in a sense, the identity of the defect. Okay. And if you look to the top left of this slide, we have another capability in our software, which is the Raman library, from which a lookup table basically of different materials that could be correspond to that defect. And in this case, she was able to identify what looks like barium sulfate, so barium sulfate contaminant. So it's clearly a foreign body that somehow found its way on this wafer. But not only are we able to identify, what the contaminant is, but we can look at the effect. And so this data that you see on the middle, the bottom of the screen, the green and blue data here, is getting this depth profiling. So on the surface, you see that defect or the contaminant, as the effect of it anyway, is a fairly extended defect. And as she probes from the surface, which is this sort of minus 0.8 microns down into the wafer, is 2.8. First, we see an offset between the two, and so indicating that this thing is three-dimensional, and it's conical. So it's large on the surface, small in the bulk of the material. So it's some kind of cone-shaped defect, and probably one could infer crystal planes, since the defect propagated along known directions. This could be used as an inference for crystal planes and stuff. But the point here is that we can uniquely identify the contaminants, and we can look at the 3D effect of the presence of either those contaminants or defects on the either substrate or epi wafers. Now, in the last slide, I mentioned you already saw us now starting to correlate multiple techniques, right? Where we showed whether it was cathodoluminescence and Raman, showing how they can provide complementary information. And continuing with that theme of multimodality, we show here the complementary Raman map of a defect, as well as the time-resolved photoluminescence map around the same defect. So as we saw in the previous slides, one can very quickly and easily show the location and type of defect using Raman. And the benefit of the time-resolved photoluminescence here is that we can also see how this defect affects charge movement around it, right? Remember that a lot of the devices that are made from this material are electronic in nature. They involve charge movement. So understanding the property of charge movement around defects is important if we're going to understand yield. What affects yield anyway. And this often, determines whether a defect is benign, that is electrically benign, or can be have a severe electronic effect, which will affect defect performance. Now, in terms of the measurement principle, the time-resolved photoluminescence is similar to steady-state photoluminescence, except that in this instance, our interest is in measuring the time decay of the luminescence signal instead of its intensity, as we would do in the steady-state measurement. So it is a time of flight measurement that can show the evolution of photoexcited charges around a defect. This is another time-resolved PL measurement for two substrates and epi wafer sample. Now, clearly, the epi layer, I'm sorry, does a lot of good in terms of reducing defect. This is evidenced by the long lifetime of the photoexcited carriers for the sample that has an epitaxial layer. You can see this blue curve and the bottom of the middle and bottom of the screen. The charge decay time is much longer compared to the bulk material that you can see the different modes in PL. You can see that the decay times are much different, and that's often indicative of the presence of or concentration of defects. Now, this is again going back to defects and contaminants. I had shown on one of the previous slides this barium sulfate contaminant, and the same thing that we're illustrating here. That you can do a coarse map on a large wafer, and oftentimes the usually PL is sufficient. You would see some contrast, like we see here on this map on the middle of the screen at the top, and we can visually see what that is, but oftentimes that's not enough. You really want to know what it is, and for that, Raman can come in quite handy, as I mentioned before. You know, most materials that are Raman active, their Raman signatures are often fingerprints of the material, so you can uniquely identify what a material is, and hopefully, if it's a contaminant, you can work your way backwards towards identifying where it came from and eliminating that from the process. Now, the last thing we are going to talk about of the three things, we have talked about stress, we've talked about defects and contaminants. The last one we're going to focus on is the yield challenges resulting from uniformity. As we said before, um, the ever drive for better yield, the ever increasing drive for yield or better yields comes with increasing sizes of the wafers involved. For silicon carbide, today's state of the art is 200 millimeter wafers, and I'm sure that's going to continue to increase. The problem, of course, is that the larger your wafer, the more challenging it is to achieve uniformity, just given the nature of the processes involved. So being able to map that uniformity for device wafers is important. And for that, the go-to tool often is things like photoluminescence because of their ease and speed of doing that type of measurement. Okay, so I will transition here to some of the other modalities that are used, metrology modalities that are used for characterizing wide bandgap materials outside of the realm of stress, defects, and uniformity. And for that, we're going to start with just basically thin film, legacy thin film techniques like ellipsometry. I will not dwell too much on this slide, except to say that, of course, ellipsometry is a well-known technique for thin film material characterization, and you can get things like the thickness, optical constants, crystallinity, and a lot of the interface effects, such as roughness and gradients. All of those can be properly characterized using ellipsometry. I wouldn't call this I know I talked previously about defects and contamination, but of course we know that there's a counter side to that where you actually want these things to be present, and so we call that's the doping more. And of course, if you look at most of the electronic devices that we are talking about, MOSFETs and the like, these are materials whose performance depend on very controlled introduction of these doping materials and at very specific concentration ranges. So being able to characterize what those doping concentrations, and of course more importantly the uniformity across the wafer, the epi or device wafer, is very important. And for that there are other techniques being used today, like there are mercury touch probe techniques, but which is a contact technique, by the way. We can do such things these days using Raman spectroscopy, which is non-contact, and of course less prone to introduce foreign materials on the wafer because of contact measurement. In this case, we're looking at two well-known peaks and the ratioing of those peaks as methods have been devised to be able to tell, and to correlate that measurement to doping concentration. Not quite related to wafers in this case, but still an elemental analysis technique that is relevant for wide bandgap materials. In this case, I'm showing our um, uh, um, um, elemental analysis techniques for things like carbon. And on this tool, basically, it's not a wafer, but in this measurement, we're looking at the ratio between free and bound carbon. It could be something that can be used for sourcing, the feedstock that goes into boule fabrication, in case that ratio is of any importance, or even any other contaminants that can be characterized out of the feedstock or out of the wafer. This technique would be relevant for that. And next year, I'll talk about our GD Profiler 2, which is a glow discharge technique. It's a sputtering technique where basically the material is spotted off the wafer, and in the resulting plasma, we can look at it's an elemental analysis technique, and it's very relevant for things like LEDs. This was very popular around when LEDs were growing strongly, because that device performance properties rely on materials lying where they need to be in the epitaxial stack, right? But we also know that there tends to be ion migration for some of these devices, and so when a device fails or malperforms, you might want to, for failure analysis, find out why, and oftentimes it's because things are showing up where they don't need to be. And because this is a depth profiling technique, we can go, spot it through the depth of the epitaxial stack, and we can see basically where different ions show up and how those ions would affect, or how those elements will affect the performance of the device. The next technique I want to talk about is well removed from just regular metrology, wafer and thin film metrology, and going now back to things like CMP process for these types of materials. And we have a whole host of tools that can be used in this technique. Of course, this is away from the fab, but of course, feedstock suppliers for epi and substrate wafers, they need to be mindful of those steps that precede what they are doing and how they can induce defects. And so sometimes going backwards is in maybe forensic analysis to figure out where things like scratch defects are coming from, and oftentimes that has to do with the CMP step. Okay, so we'll transition here to the last part of my presentation, which has to do with some of the practical challenges that are involved in some of the measurements that I have just shared with you, and how a user needs to be mindful or address or look for their vendors to address these types of challenges. The first one I want to talk about is, again, mindful of the fact that the epi wafers, the substrate wafers that we are talking about now are getting larger and larger. It used to be 4, now 6. And we're going on to 8-inch and beyond. And so the larger these substrates get, the harder it is to do the types of measurements that I've just shown in the previous slide, right? Because we are looking oftentimes, especially with things like defects, we are looking at things that are, micron level, right? Sometimes they're even sub-micron. Now, trying to get that level of spatial resolution on a 200 millimeter wafer uniformly across is not an easy task. And so, because you suffer from little things, like you can see here, I'm illustrating two things, tilt and bowing. So in this case, tilting, that is, when a wafer is tilted, either physically on the stage or some bowing or whatever causes the inability to define a perfectly perpendicular plane to the laser excitation. Then as you traverse the wafer, your focal point changes. And I just showed you in a previous slide one of the measurements that we just recently did here, where Fran was probing through, a defect from the surface a few microns below to characterize the geometry of the defect. Now, if you have these kinds of artifacts where, a tilt or bow, it makes it really quite hard to do that kind of measurement across the entire wafer. So one needs to be mindful of additional techniques to correct these types of artifacts. So you can see here, for example, this wafer is actually perfectly uniform, but what you're seeing in the measurement in the middle here is really just an effect of tilt. And so vendors like us, we have techniques to correct for this. So we have in our software, for example, what we call multi-point active tilt correction. And if you're interested, we can always talk about these kinds of things offline. The next thing I want to talk about is just speed, right? So again, wafers are getting larger and we need to probe them at even more finer resolution. So if you're going to do that over large wafers, it can be very, very time consuming. And so most of these types of measurements, these optical spectroscopies, are done by rastering a beam across the wafer and with the stage moving or the beam being rastered independently. So I illustrate here with the rastering. So the image, the video that you see on the left side of the screen, that's your basic normal rastering, right? You go point to point and you take a measurement, a spectrum at each point, and you generate a composite map. Now, if you did this as you see here on the left side, for a large wafer, now this is why some measurements speeding up mechanism. And of course, vendors like us have come up with these types of speeding up mechanisms. We have technologies such as Swift, we call it, or dual scan, or newer incarnations of these technologies that can make the mapping process quite fast. This is actually what I just said in the previous slide, so I'm going to skip that. And this illustration here is just showing you how we can achieve this. And this is a key point for us here at HORIBA, because if for some of these measurements, if you cannot do them quickly, it becomes somewhat irrelevant, right? So in this case, I'm illustrating here 2 points. One of our sort of this speeding up techniques. This whole illustration here to the left of the screen is just showing you how we can raster the beam without moving the stage, right? Now using galvo mirrors to raster the beam across the sample without moving the stage. And to the right of it, what we show here is this dynamic beam shaping, because the needs here actually change, right? If you are looking for high resolution stuff, then you want that very, very finely focused beam to look at a very small area. So in that case, you go for this tight focusing, get the high resolution, and you can raster across the beam, the sample very quickly. But if you are looking at something like uniformity, well, you don't need the resolution. So do you need to go to a different tool? No. What we do here is we offer some type of dynamic beam shaping. The same beam, the same optics, we can go from very tightly focused beams to get your high resolution spatial measurements for things like defects. And then, that beam can be broadened somewhat to give you, to interrogate a larger area of the sample and therefore giving you speed when you don't need the high resolution. And the final thing I'm going to talk about is this this challenge of looking at very, very small things, especially when the need is to use more than one instrument, right? I've mentioned before that necessarily most of this work is multimodal. No one technique can tell you everything you need to know about your sample. So it's very common that you would measure, execute one technique on one instrument, move the sample to another instrument, another modality, and to learn something else about your sample or a specific location. Now, I must clarify that several of our tools are intrinsically multimodal, meaning that the sample stays on the same stage, and you can measure, you can do Raman, PL, and many other techniques on the same stage. But in those instances where you have to move the sample from one instrument to another instrument, for example, going for say a Raman instrument to a cathodoluminescence instrument, well, those are physically two different instruments. The challenge then becomes, you've located something that is a micron level feature or sub-micron level feature on one instrument or across a 200 millimeter wafer, and you need to take that thing to another instrument and locate that 1 micron or so feature. That in itself can be a very time-consuming step, right? And so what we've come up with various technologies to facilitate this, to automate the coordinate transformation from one instrument to another instrument to facilitate the relocalization of features of interest. We have things like this technology called Navix. It's basically a nano GPS equivalent. So on one instrument, a feature of interest can be tagged, right, and the coordinates saved. And how it works is that we were able to place this what we call nano GPS tags on the sample, or at least a carrier, and that is the device that is used to reorient the sample when we go from one instrument to another. And what this enables is really the ability to achieve even global cooperation, right? So many of our customers, many of you on this call work for global companies that span the globe basically. And so you can, and some of the modalities are not in the same location. So you can do a measurement in the US, ship the sample to Europe, to Japan, to China, for your colleagues to do complementary measurements across different platforms. And the work becomes very easy because the ability to locate those sample areas of interest has been vastly improved with these technologies. I indicate what an example of this in the lower left or lower right of the screen, where we specifically do a photoluminescence map on one of our spectroscopy instruments, optical spectroscopy instruments, and these are gallium oxide nanorods, and same samples, which are actually sub-micron across. These samples are moved onto an electron microscope with a cathodoluminescence modality, which is the picture that you see on the left-hand side. The picture on the left-hand side is the CL image. The picture on the right-hand side is the PL image for the same thing. And of course, these things tell different stories about the sample, and that's why you want to do these complementary measurements. Okay, so that's the last slide for me, and I'll just summarize here that hopefully in this presentation you've picked up this variety of modalities that are available from many other vendors, and definitely from HORIBA. In our case, one of the uniqueness is that we actually have several of this on the same instrument, and furthermore, we are probably one of the companies that can offer these modalities from the R&D side and increasingly over to the production side of the business. So we can be there to walk the journey with you when you're still doing material research, process characterization, process improvement, all the way to when you're approaching the fab for QC type measurements. So I'll stop here. I'll be happy to address any questions that you have. And thank you for taking the time to join the webinar.
Dr. D, I'd like to welcome you back up on camera here. Yes, thank you for your excellent presentation. It is now time for our live Q&A portion of our webinar. Now to our audience, if you haven't already done so, submit those questions in the Q&A box, and we will answer as many of your questions as we have time for. So, Francis, we have so many great questions that have already come in. I am going to just dive in here and answer them and ask them for you. To you, let's just start right here. For defect characterization, are your systems able to make low temperature measurements? And if so, are you limited to specific cryostats?
Yes, first of all. So we have systems that can quite readily adapt to different types of cryostats. In fact, I think we are compatible with many of, actually all, I would even hazard a guess, all of the major cryostat manufacturers. So we'll be glad to talk to anyone who's interested about how to approach that. And of course, I mentioned in my presentation, one of the three main features for this type of characterization is defects, and that's usually where people do low temperature work. So we have very good experience with doing those types of measurements.
Very good. Thank you. And Francis, how fast are typical measurements for Raman and PL?
Um, so it depends on the objective, and I would say that so I've mentioned two things: uniformity and defects. Uniformity often, and again, depending on what you're measuring for uniformity, often we don't need very high resolution. I just throw some numbers out there. We're able to map, for example, a 1 millimeter grid sized grid on a map on a 2-inch wafers on something like 2 minutes. Going up to 300 millimeters, it easily can be 15 minutes or 20 minutes or something like that. But oftentimes there's a need to look at some feature with uh, very, very high resolution, and depending on that area, it can be from a few minutes to several tens of minutes and even hours.
Francis, can the systems show on the map only 12-inch wafers or a range of wafers, say from 2 to 12 inches?
Yeah, most of our systems can go up to 12-inch. So we have different types of chucks that a customer can use, but the stages intrinsically can go from 2 to 12 inches.
Now we have several questions coming in about autofocus. Can you perform autofocus at every point in the map?
Yes, but I would caution that that can make the map also very slow. It's a trade-off that needs to be made.
And on the systems, can it show a combine of Raman PL and TRPL on one system?
Yes, we do have systems that specifically have those three modalities because those are the commonly used ones for wafer characterization. So they can be add-ons to other some of our other platforms, but we do have systems like the SMS that has um, natively can accommodate those three modalities on the same system.
Very good. Now, next question. When scanning the laser across the ROI instead of rastering the stage, is there any change in the Raman profile in terms of individual peak heights?
Sorry, can you restate the question? I don't think I understood it.
I sure can. It
Mm.
says when scanning the laser across ROI instead of rastering the stage,
Mm.
is there any change of Raman profile in terms of the individual peak heights?
No. So I think that question, behind that question, maybe is a concern about distortion in the beam, because when you're scanning the beam, you're tilting the beam basically. I think that's the concern, but no, that shouldn't. Of course, the range of rastering is calibrated to basically eliminate those distortions.
Excellent. And we have time for a few more questions. Since these are wide bandgap materials, one typically needs UV or DUV excitation. Are your systems customized in any way to function optimally in this range?
Absolutely. And I did not mention this in the last part of the presentation that talks about the challenges. And definitely for wide bandgap materials, one of the challenges is dealing with systems that have this UV excitation for two reasons. One is that well, pretty much everything is absorbing in the UV, so the optics and the conveyance mechanisms for UV have to be specifically designed, and so that is the case for our systems. And of course, UV radiation by itself, it's also can be hazardous, and so the systems have to be special in a way.
Okay, good. And is the Navix technology unique to HORIBA systems, or can I work it across different platforms?
Oh no, it's an open platform tool. Of course, different systems we have requirements for applying the technique, but it's an open platform. So the idea is that we can not only on HORIBA systems, but across different vendors who have adopted that technology, you can seamlessly go from tool to tool to facilitate your measurements.
And
I would by way of that comment add that that's one of the reasons why so some of our customers actually advocate for other vendors to to adopt this tool because it facilitates the work. So if it's of interest, we'll be glad to talk to you about it.
Excellent. Thank you so much. And we have time for one more question. And let's see, let's go with, let's see, can your system accommodate different lasers for different types of materials?
Yes. Um, so why would you want to do that in the first place? So I'll give you two reasons. One of them, for example, taking something like PL, which is you basically need to have an excitation that matches or is above the band gap of the material of interest. So that pretty much drives the need for different laser wavelengths. And then secondly, we're looking at epitaxial structures, and sometimes you want to selectively probe some layer and not excite in another layer. So especially if that's a surface type layer, you want to have something that will not penetrate deep into your epitaxial stack or go into the substrate. So you want to go with shorter and shorter wavelengths that absorb, on a very thin surface on the of the wafer. So these are all drivers for having different types of lasers on your system, and certainly our systems, all of them practically can accommodate different types of laser wavelengths.
Dr. D, thank you so much for your time today and for addressing some of the unique challenges in doing measurements for wide bandgap semiconductors and how to overcome these challenges. We do want to thank LabRoots and our sponsor, HORIBA, for underwriting today's educational webcast. Dr. D, before we go, do you have any final comments for our audience?
Yes, thank you, Christina, and I just want to express my thanks for the opportunity to share this information with your audience, and thank the audience for participating as well. And just concluding that wide bandgap materials is a very exciting time for this material system. You see them everywhere, and we just came from the ice cream conference in North Carolina a few months ago, and the crowd there was very indicative of the level of activity that is happening around these materials. So we are excited and interested to be part of that ecosystem, and we're doing a lot to support those of you who are practitioners. Um, uh, uh, the challenge at the moment is yield improvement, quality, of course, and the yield to go with it. And many of the things that we've shared here are things that, in fact, I think some of them are not even common practice yet, but they will be. And we'll be happy to accompany you on that journey to improve your metrology with the goal of getting better yields out of what you do. So thanks again for the opportunity, and we hope to connect with you in the future.
Thank you, Dr. G. And I too want to thank our audience for joining us today and for their interesting questions. There were some questions we weren't able to answer today, and additionally, those that come in during the on-demand period, they will be addressed by our speaker via the email address you provided at the time of registration. Now, today's webcast can be viewed on demand, and LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. To all our friends out there, thank you for joining us. We hope to see you again